All right, class, welcome to section 6.5, solving exponential equations and applications. So we're ready to solve those exponential equations. We've solved a couple of them once we started talking about logs and switching from exponential to logarithmic form, I mentioned. But now let's just concentrate straight up just on solving exponential equations and their applications. Okay, so clearly an exponential equation will have the variable in the exponent. This is how we recognize that we're dealing with an exponential equation. As you see, the variables are every single time in the exponent, right? Not in the base, okay? All right, so let's start with an easy one we've discussed already. 2 to the power of what equals to 8? Now, of course, you already know that this x must be a 3. 2 to the power of 3 is 8. We've looked at this equation forwards and backwards from different angles. However, once it doesn't become as obvious, as you see in the next examples, what x would be, what could be a method of solving such an equation? So the easiest one would be to say, okay, 2 to the power of something equals to a number. Can we write this number as a power of 2 itself? And we know that 8 is 3 2's multiplied together. So 8 is 2 to the power of 3. And now as you see, I have two expressions that equal to each other. The bases are matching, therefore the exponents must be matching as well. So therefore, x must equal to 3. All right, and done. So here it is again. 3 to the power of x minus 2 equals to 9. Okay. Now, same thing. Can we write both sides of the equation in terms of the same base? Well, we already know that 9 is 3 squared. So therefore, these two exponents must be matching because the bases are matching itself. Really, what we're doing is to undo a base of 3, we're logging both sides with a base of 3. It's kind of like looking at equations that said, hey, if the square root of x equals to the square root of 2, guess what x is? Yeah, so we're performing the same operation on both, but really what we're doing is we're squaring both sides, and that's what makes the squares go away. Same thing here. Really what we're doing is we are logging both sides with a base of 3, and log with base 3 of 3 goes away, and then all you are left with is just the exponent. So easily, therefore, x is 4. Now you don't have to write log with base 3 of 3 on both sides to show that the bases go away. It's totally fine. It's clear, again, just as here, since the same operation has been performed to both x and 2, that x must equal to 2. But technically, that's what we're doing. Okay. This equation, next equation, is very straightforward, as you already have the bases that are matching. So therefore, the exponents must be matching as well. And we transform our exponential equation into a very simple linear one. So we'll get the x's to one side, the constants to the other. So there we have 2 equals to x, and done. All right. Now, if I look at this equation here next, I see that actually 16 is not a power of 8. It's a double of 8, but it's not a power of 8. 8 squared would get us immediately to 64. However, both 8 and 16 are powers of a common base, which is 2. So we can write 8 as 2 cubed. And we can write 16 as 2 to the power of 4. And if you have trouble with this, you can simply take your calculator, multiply a bunch of 2's, and see how many 2's it takes to get to 16 and how many 2's it takes to get to 8. Now we're going to use a rule of exponents that says a number raised to an exponent to another exponent. What you get to do is multiply the exponents. So the 4 gets multiplied to x plus 1, and the 3 gets multiplied to x plus 2. And now you have it. The bases are matching. Therefore, we can drop them. Again, we log both sides with a base of 2. That's what makes them go away. And I'm now left with just the simple linear equation again. Okay. So I'm distributing the 3 to both x and 2. I'm distributing the 4 to both x and 1. And same thing, this is a linear equation. We'll get the x's to one side, the constants to the other. And it so happens that we also get the x's too. Easily done. Okay, so once we have those bases matching, then we get to go. So here I can try another one. 2 to the 5x. Again, 2 is already the lowest base it could be. You cannot rewrite 2 as a power of any other number but 2. But the square root of 2, I'm bringing this back to remind you one more time that a square root means a 1/2 exponent. So therefore, since the bases are matching, the exponents are matching too. So when I divide both sides by 5, this kind of looks funny, but you can take your calculators. 1/2 divided by 5. To divide by 5, by the way, is the same thing as multiplying to 1/5. Okay, so that's why you get 1/10. But you can check it with your calculator as well. All right, so let's see here again. Can we find a common base for 1/5 and 25? Okay. So 1/5 is 5 to the power of -1. Remember, negative exponents produce fractions. 25 is easily 5 squared. So again, the first thing we're doing is rewriting it all in terms of a base of 5. And then we get to multiply the exponents. Okay, so -1 times x is -x, and 2 times x plus 3 is, well, that. So I'm going to now match up the exponents since the bases are the same. Get the x's to one side. Again, it turns into a nice linear equation, easy to solve. We've done plenty this semester. So x is going to equal to -1, and done. All right, now, what if we cannot write both sides in terms of the same base? So as you see immediately here, 24 is not a power of 3. It's a multiple of 3, but 3 times 3 times 3 times 3 won't get you a 24. Okay, so the only way here is to use a logarithm. Now, if you remember, we switched from exponential to logarithmic form, and we wrote that the log with the same base as the exponential of 24 equals to x. All right. Well, there you got x by itself, right? Now, all we have to do is, this is a number already. It's an exact number. It's kind of like leaving the square root of 7 as an answer. That's an exact value. I'm not exactly sure how much it is. I know it's about a 2 point something, but what it is, I'd need a calculator to find. So that's, again, however, the exact answer. Now, to figure out logs, we have used our calculators to find a log of any base, and we simply switched it to a common log or a natural log. So that's either ln of 24 divided by natural log of 3 or common log of 24 divided by common log of 3. So if I'm taking the calculator, it doesn't really matter which button do you choose, either the LOG button or the LN button, but you better use the same one twice. So as you see, it's 2.89, so on and so on. So again, maybe the instructions will say how many decimal places we want in the answer. Otherwise, you can choose to stop wherever you want. So 2 decimal places, I'd say, is pretty good. But fine, I gave you 3. So, by the way, that's the same way you could have solved any of these equations up above. If we didn't know the 8 is 2 to the power of 3, I could have taken that expression and switched it to a logarithmic form. So there you go, log with base 2 of 8 is x. How do I find log with base 2 of 8? I'll put in my calculator, ln of 8 divided by ln of 2, or again, common log of 8 divided by common log of 2. Your calculator would have told you the answer is 3, okay? All right, so that's one way of solving these equations. Another way would be to go, since I have to go straight to my calculator, we can immediately log both sides of it, and we don't even have to do this swapping from exponential to logarithmic form. We can immediately log both sides of this equation with one of the logs that we have a button for in the calculator. So for example, I can log both sides of this problem with a, let's say I'm picking a base of 10, so I'm using a common log. Okay. All right, well, what does a common log do? It's going to force, based on the rules of exponents, it's going to force that exponent up front as a coefficient. All right, so now x plus 1 is common log of negative 2 divided by common log of 3. And now I can straight up use my calculator to find this answer. Okay, and of course, then we're going to need to minus 1 from x. However, maybe you guys were already up in arms. Hopefully you were. If you put log of negative 2 in your calculator, what is your calculator going to say? No real answer, or actually no answer, period. It's not even that, it's imaginary. So even, yes, then let's just say you didn't realize, and you went on and you copied the whole thing. Same thing, your calculator is going to say, no, it's not possible. And of course it's not possible. I could have told you that from the beginning. An exponential expression can never equal to a negative number, okay? So we looked at the domain and the range of the exponentials, and we already remember that an exponential function is always above the x-axis, so it's never going to equal to a negative 2. If you didn't notice it there, great. Immediately put it here. Can you have a negative number inside a log? Absolutely not. Right here, this one fails immediately. We already talked about, and you've done plenty of homework hopefully on it, that you cannot have negative numbers inside the log. So it doesn't matter how far you take this equation, even if you just go all the way to asking your calculator for answers, it's going to strike at some point, and it should be clear then that's not going to be possible. So there's no solution to this one. So be mindful of, again, the domain of a logarithmic function, or again, the range of an exponential function, which have to be positive numbers only. All right. This one here should work though. So immediately I'm going to log both sides. And again, I know it works because equals to a positive value. Okay. So when I log both sides, the 2x minus 1 comes up as a coefficient. Oops. Times ln of 15 equals ln of 3495. And so therefore 2x minus 1 is going to equal to natural log of 3495 divided by natural log of 15, which I'm going to put in my calculator and approximate and again, oops. You could have, again, used the common log button or this one, it doesn't matter. So the answer is about 3.01. Okay, so there it is. To further solve this equation, what else do? We add 1 to both sides, yes. So that's about 4.01, and then divide by 2, and that makes x about 2.005. There you have it. Very, very close to 2. Again, even if you would have just simply from here switched this to logarithmic form, log with base 15 of 3495 equals to 2x minus 1, it would have been just about the same. Again, switch to logarithmic form. However, I don't know how to find this log. So to find this log, what do I have to do? I have to change the base. So let's say I'm changing it to a natural log base. So that's ln of 3495 divided by ln of 15. So as you see, even if you take this route, let's switch the exponential function into a logarithmic form and then use the change of base formula, we end up in the exact same spot that 2x minus 1 is going to equal to the natural log of divided by natural log of, and that's how we continue and solve this problem, right? So either way, you end up in the same spot. You can choose how you want to solve these problems. Here it is. Now, this equation here has a little bit extra layer because as you see, the exponential is not yet by itself. So we have to get to the exponential first. So let's clean it up. I'm going to divide by 20 first, and I'm going to get a 5. Now, if you remember, E is our Euler number that we have a button for on the calculator. And this time it's very clear which log I'm going to use on both sides, and that should be the natural log, which happens to be the inverse of the natural exponential function. So a natural log and a natural exponential function, remember ln is a log with base e, so they immediately cancel out. So I'm left with natural log of 5, which we can find using our calculator, equals to 2t. And now to get to that t, I'm going to divide by 2. So natural log of 5, always close the parentheses, divided by 2, because otherwise your calculator will think that you're dividing 5 by 2 and not, in other words, 2.5. And then not that the natural log value gets divided by 2. So 0.8047 here. Four decimal places. Okay. So same thing we'll do here. Before we even get into this exponent, there's lots of stuff that we get to undo. We can undo the addition with a subtraction. We can undo the multiplication with a division. And finally, we can undo a base with a logarithm. So 2x is natural log of 7 over 4. Okay. So x is going to equal dividing by 2 or multiplying by a half. By the way, this is the exact value of the expression. But if we want an approximation, so x, this is a number. 1/2 times natural log of 7/4 is kind of like my answer is 2 squared of 3, right? That's the exact answer. However, if you want to know about how much this number is, I'd have to use my calculator. So what is 1/2, or in other words, 0.5 times natural log, of 7 over 4. It already opened the parentheses nicely for me, so I didn't have to open another one. So the answer is 0.2798. Which is an approximation because we did cut off a bunch of decimals. All right, and this last one is a little tricky because you see your exponential coming up in 2 different places. However, this very much looks like an quadratic type of equation. So same as we even solved equations that had x to the 4th plus 5x squared minus 14. Which looks very much like an x squared plus 5x minus 14. So all these types of equations that look very similar, they look like quadratic trinomial types. We call these of the quadratic type. So we can try and solve this problem by factoring. And let me show you easily. E to the x squared, it comes from an e to the x times an e to the x, right? Same as with split an x squared into an x and an x. And now I just have to find numbers that multiply to 14 and subtract the b5, which are 7 and 2, plus 7 minus 2. And you're very welcome to distribute these parentheses, and you see that you get an e to the x times e to the x, which is e to the 2x, minus 2 e to the x, plus 7 e to the x, which is 5 e to the x, and then 7 times negative 2 will get you there you go, writing it back. It would get you that negative 14. So here are my 2 choices. Either e to the x plus 7 equals to 0, which makes e to the x equal to negative 7, which if you remember what we said earlier is not possible, as an exponential function cannot equal to a negative. But let's say you didn't know that and you went on to use a log. Hopefully by now you would have noticed, wait a minute, I can't have negative numbers inside the log. But if not, put in your calculator and ultimately you'd get saved. Okay, so here it is. Either or e to the x is equal to 2, which is definitely possible. So when I switch this into logarithmic form, so log with base e of 2 has the specific name natural log of 2, which you can of course put in your calculator and get 0.6931. Okay. So here are the answers. Okay. And there's that. Okay. So in the applications we're going to do next, the first one hopefully you recognize from section 6.2 when we talked about exponential functions and we talked about compound interest and we developed the idea of continuous compounds. So in other words, money growing at all times, constantly figuring out the interest and reinvesting it. So if you remember that formula, is P times e to the RT, where P is the principal, the amount of money that we started with, right? So the principal is really the initial amount of money. That's what we're starting with. Whether we borrow it or we invest it, that's what we're starting with. A is the amount you're going to have at the end of these T years, right? But this does not always have to be applied to money. It can be applied to chemical compounds. It can be applied to bacteria. It can be applied to populations of humans or cats, right? It can be applied, again, there's a chemical compound, carbon-14. So anything, actually, any exponential equation can be written in, I'll put it in blue, as an exponential function with base e. You can take any exponential function with any base and switch it to a base e. So I'll switch it slightly a little bit. Now again, whatever it is you're starting with, whether it's money, initial amount of money usually is called principal. But you don't have to, again, talk about money. It could be about anything. It's the same formula, right? So let's just say instead of a principal amount of money, you have an A naught, we call it an A0, which is the initial amount of bacteria, whatever it is. But it's growing at a rate of, or it's decaying at a rate of, for some time t, at the end you will have this amount, whether it's amount of people, amount of chemical compound, whatever it is, amount of dollars, okay? So we're following the same formula, really. So let's start with this. It says an initial amount of $6,000, we call that principal, grows at 5.5% compounded continuously. Therefore, we need to use the continuous compound formula, right? How much money will be in the account after 4 years? So we know that the time is 4 years. Great. So all I have to do is put all these numbers in my calculator. 6,000 times e to the power of, now remember, you don't write 5.5, it's 5.5%, so 5.5 per 100, in other words, divided by 100, and then times 4. So what is 6,000 times e to the 6,000 times e to the power of 0.055 times 4. That's it. So that's the amount of money you'll have, 7,476 and 46 cents. Okay. In 4 years, your money grew by $1,476. Great. Now it says next, how long, that's a matter of time, will it take for the $6,000 to double in value? What does that mean? That means that the $6,000 you have is going to become $12,000. Yes, so how long will it take to double our money? So the rate is still 5.5%. But what we don't know this time is the time, right? How long? So time is missing in this formula. But what we know this time is that we want to get to $12,000. Great. So we've just been solving some exponential equations with the base of e, and we're going to get to solve a lot more. The first thing we're going to get out of the way is the 6,000. So when I divide both sides, by 6,000. I'm going to get a 2. Okay. And so again, to get rid of a base e, we're going to use a log with base e. So we're going to switch it to logarithmic form. So natural log of 2 equals to that exponent. Okay, so we log both sides, if you want to think about it, with the base of e, and then that makes the base of e go away. And so finally, time, it's going to be natural log of 2 divided by 0.055. So again, be very careful closing the parentheses. So the natural log of 2 is going to be divided by 0.055 and not the 2. So 12.6 years about. So it'll take 12.6 years to make the money double. In other words, get to 12,000. All right, one more time. How long will it take for the 6,000 to grow by 50%? To grow by 50% simply means that you are going to make your $6,000 grow to 50% of 6,000. In other words, half of 6,000 is 3,000. So you want it to make it grow by 3,000. In other words, you want to get to $9,000. You're not losing your money, right? But you're adding to your 6,000 half of it, right? So you'll get to 9,000. So when you divide both sides by 6,000, you'll get this 1.5, which is really 150%. 100% of 6,000 is 6,000, so it stays the same, yes? But to add 50% means you get to 150%. So same thing, we're going to log both sides with a natural log. And so 0.055t will equal to ln of 1.5, where t is natural log of 1.5 divided by 0.055. So 7.37, so about 7.4 years. Will take to get there. All right. Now the question is, what if we started with $1? How long will it take for the $1 to double at the same interest rate? So we started with $6,000, and it took us 12.6 years to double this amount. So what I want to show you is that if we start with $1, so in other words, our principal is just $1, and we want to know how long will it take for the dollar to double, that means we want $2, yes? And again, let me not make it as looking like an L. This is an E. So the point is, fine, whatever I'm actually starting with, the first thing I would do is divide both sides by it. So as you see, I end up with the same exact equation we had up above right here. Okay, so actually the point of this next problem, so again, 0.055t will equal to natural log of 2, and then t is the natural log of 2 divided by 0.055, which as you see is the same exact equation that we solved above. Okay, make it equal just so I don't think we get something else. But the point is that it really doesn't matter what amount of principal we're starting with. The doubling time of it is going to be the same, because the first step we do in this problem is divide by that p-value. And so same thing here. If we start with $6,000, and we want to increase it by 5%. As you see, as soon as we divide that P away, we end up with 1.5. Yes, so it does not matter what amount of money we're starting with. The doubling time is the same. So it takes just as long to make $1 into $2 as it will take to make 1 million into 2 million. So you might as well start with a million, I'd say. Okay. You have a lot more at the end. So that's very nice and very interesting how that works. Okay. All right. So here's another problem. It says $1,000 grows to $1,500 in 3 years, compounded continuously. So again, that simply means that we have to use the compound interest formula. Okay. And what do we know in this formula? We know that we're starting with 1,000. We know we're going to end up with 1,500. So that's P, that's A. 3 years, so that's time. And so what we need to do is find the interest rate. So R is what's missing this time. Okay. All right, so again, I have to get into this exponent. Before I get there, I'm going to divide both sides by 1,000. So I'll get that 1.5 is e to the r times 3. Now I'll get rid of e, which means I'm going to use a log. So natural log of 1.5 is r times 3. So again, I'm logging both sides with a natural log. That makes the natural exponential function go away. And so the last thing to do here to get to r is divide by this 3. So whether we know the rate and want to find the time, or know the time but want to find the rate, it's the same exact process. So what is natural log of 1.5 divided by 3? 0.1352. So again, remember, rate is an percent kind of number. So again, to attach the percent symbol, you must go backwards and multiply by 100%. So 100% is 1, really. So it's the same value. It just has a percent symbol attached to it. Okay. A chemical compound decays at a rate of 2.5% compounded continuously. Find the half-life of the compound. So here it is. Now we don't necessarily know what amount decays. Let's see, what do we know? We know that it's compounded continuously, so we're kind of using the PERT formula, right? Again, it doesn't have to be about money, but any amount at time 0 will grow to some kind of other amount. So we want to find the half-life. Now, anything that grows will eventually get something that we call doubling time. So anything that grows at some point will get twice as much, will double, right? We'll get to twice as much as we started with. Anything that decays will eventually get to half of what it is. So half-life is the time it takes to be left with half the amount. And again, on the flip side, when something grows, we call that doubling time. Okay. So if the amount we have will be half of what we left with, again, all we know here is the growth or the decay rate. And by the way, because it says decays, we have to put a minus because it's not a growing quantity, it's a decaying quantity. So that exponent's going to be negative. And again, as I explained, it doesn't really matter what we start with, because the first thing we're going to do is divide by this value, and you just end up with this half, right? Whether it's, again, doubling means you'll end up with a 2. Half-life means you end up with half of it. So again, we're going to log both sides, or if you want to think about it, is turn it into an logarithmic form. And so same thing, t is going to be natural log of a half, or 0.5, divided by negative 0.025. And by the way, I just want to show you a natural log of a number less than e is going to be a negative value. So this is why it actually works so well. We have this negative value, and we divide it by a negative 0.025. If you remember, that was the decaying rate, and it has to be negative because it says decaying, and therefore we end up with a positive answer. So 27.73. Okay. And we're just going to do this a few more times the same way. It says a research student is working with a culture of bacteria that grows at a rate expressed by this function. So this time we are given the function, the expression. As you see, it's a continuous growth, the base is e, where t is in minutes. To the nearest whole number, what is the population size after 45 minutes? So time is in minutes. When the time is 45 minutes, simply means to plug in 45 for t. So yeah, as you see in this problem, they've kept quite a lot of decimals up there at the rate. Didn't cut it too short. But all we have to do is put this number in the calculator, 1350 times e to the power of something. I don't remember anymore. I knew it was, I forget. So 0.03466. 03466, but we multiply this to the 45 minutes and press enter, and there you go, 6422.5. And this is bacteria, amount of bacteria. Okay, that's how much we have. Now next question, it says find the time, so this time we have to find t, when the population will be 8 times the initial value. So the population will be 8 times this initial value of 1350. The rate is the 0.03466, but it's the time that we're missing this time. Okay. So this time we don't know the time, but we know the amount that we want to get to is going to be 8 times. It's like the doubling time or whatever, but it's not the doubling time. It's the 8 times time. And don't even bother multiplying these numbers together, because the first step in solving this equation is to divide, to undo this multiplication by dividing by 1350, so you end up with 8. And again, to get to t, as we've done already quite a bit today, we're going to log both sides and then divide by this number that the time is multiplied to. So I have natural log of 8 divided by 0.03466. So about almost exactly 60 years. Oh, not 60 years, 60 minutes, sorry. So just about an hour, right? So here it is. Okay. The population of a city is modeled by this equation. So again, here it is, where t is measured in years. If the city continues to grow at this rate, at 25% every year, how many years will it take for the population to reach 1 million? So the amount that this population should reach is 1 million. Okay, and here it is. There, immediately we get to work and we divide by this number and then log both sides. So what's a million divided by 256, and I've already forgotten, 114. Okay, 3.90. And again, to get rid of e, we're going to log both sides. And then divide by this coefficient. Okay. So natural log of, I'm going to copy a little bit more since I am back on my calculator with all these numbers in front of me. Divided by 0.25, not 0.25. So about 5.5 years, 5.45 years, let's just say. Okay. It says a population of cats increased by 50% in 2 years. So immediately the amount we have is going to have increased by 50%. So to have increased by 50% means that you have a 1.5 times left. In other words, 150%. The situation is modeled by an annual growth rate compounded continuously. Which formula could be used to find the annual rate according to the exponential growth function? So of course, for this, we would need to know that specific rate. Okay, so the time is really what drives these populations, but it's the rate that we need to find. So we know it took 2 years to make this population increase by 50%. So again, if we divide now both sides by A naught, by this initial amount, whatever it is, start with 1 cat, okay? The first thing it's going to happen, it's going to divide out. So let's log both sides and then divide by 2. So R is natural log of 1.5 divided by 2. So 2.027, I'm going to write 0.2027, which is 20.27%. But again, to write the function that describes the situation, whatever amount you're starting with, we don't know, but we know the growth rate is 0.2027 about, and then t. There it is. This is the formula that could be used. And here, last time one, the half-life of carbon-14 is 5,450 years. So again, the time it takes for an amount to be left with half of what it was is 5,730 years. Okay. So we want to express this amount, the amount remaining, as a function of time. So same as in the problem above, we do need to find that rate. In this case, it's going to be a decaying rate. So same thing, we're going to divide both sides by A naught. We're going to get rid of E by using a log. And now we're going to divide this log of 1.5, I'm sorry, 1.5 of 0.5, or a half, by 5730. It's going to be a tiny, tiny number, but as you see, it's a negative number. And so that e to the negative 4 simply means that you're going to have to move the decimal 4 places left. It's like scientific notation. So 4 places left. Let me try and copy this. So it says take this e to the negative 4 and move the decimal 1, 2, 3, 4 places left. So therefore, you're actually going to have a 0.00120. I'm sorry, I'm just going to write 21, round it up there. So there's quite a lot of, I'm going to round this up. So there's quite a lot of decimals there, but again, carbon-14 is a chemical compound that decays very, very slowly, as you see. This is not big, right? It's almost nothing. But it's still decaying, so therefore there's still quite a lot of quantity left after millions of years. So we use something called carbon-14 dating to find the age of fossils, because they will still have some left millions of years later. So how long will it take for the amount of carbon-14 to reach 20% of its original amount? So whatever you started with has to be only left with 20% of it. But now we have this decaying value. And this time we have to find t. So last time, 0.20 e to the negative 0.000121 t. Yes, so again, divide both sides by this initial amount. Log both sides with a natural log. And then divide by this value. So t is going to equal to natural log of 0.20 divided by natural log of this negative number, 0.00012. We said 1. We rounded off all these 0.096 to a 10, basically. What happened here? Oh. No. Okay, it's not natural log, sorry. Divided by that value. Negative. I need a negative there. Okay. So 13,301 year. Yeah, there's no log on this. It's just dividing by it, of course. Here it is. All right, so we did quite a lot of the same kind of problems over and over and over again. So hopefully you guys are experts now.